In this section of the course, we're going to prepare the groundwork for our investigation of calculus. We're going to start looking at functions of one variable and the related concept of limits. Now, of course, you've seen many functions before and are familiar with the concept of functions. So let's go over the basic idea again, just to recap and introduce different types of functions and different ways to define functions. So in general, a function is just a rule which turns one number into another number. So the rule, for example, where I want to square a number is a function where I take a number like 3, square it, and that returns the number 9, so on. Other examples are things like volume of a sphere. V is 4/3 pi r cubed. If we vary the radius of the sphere, that becomes a function which we can write down as v as a function of r. Other examples of functions you'll see in physics all the time are things like acceleration of things over time. So the acceleration of a car over time can be described as a function. We might write that as a as a function of t. Typically, we visualize these as curves in some sort of diagram, typically on a Cartesian diagram. Here's some examples of functions you're familiar with. Let's just see if we can identify them. So here's a bunch of functions all drawn on the same Cartesian plot. Let's just see if we can pick them out. Let's start with the exponential function. Where can we see this on the plot? Well, the exponential function is a function which at very small, very negative x tends to 0 and at large x tends to infinity. The only function on this picture that looks like that is this curve here. So this is a function exponential. Let's try and pick out the other functions in here. Sine and cosine. Now we know those functions oscillate. Now there's two oscillating functions on this graph. This curve and this curve. What else do we know about sine and cos? Well, we know that sine of 0 is 0 and cos of 0 is 1. So we can therefore pick out sine. It's the oscillating function which goes through 0. And then cos is the other one. Cosine is the one that passes through 1 at the origin. So that leaves just two more. Logarithm and square root function. Now these perhaps look a little bit similar on the graph, but they have important distinguishing features. The square root function is always positive, whereas a logarithmic function can return negative numbers as well. And that's a very clear way to find these two functions on this graph. This curve here is always positive, so we can identify that then as the square root function, leaving the final curve as the logarithm. We'll go over the proper definitions of these as we go. So generally then, a function is defined as a rule which turns one number into another. We might write this as a function f as a rule such that f takes some numbers in r in the real line and maps them to other parts of the real line. So all of those examples that we've just seen do that, except it might sometimes be just a subset of r mapping to another subset of r. And that's known as the domain mapping to the range of the function. So let's in fact recap a couple of examples. So if we recall these couple of examples from just a moment ago, the square root function and the logarithm function, these actually have different domains and different ranges. So if we think about the square root function to begin with, that takes all positive numbers and returns a set of positive numbers. So this we can think of as x must exist in the interval 0 to infinity, and it maps onto the interval 0 to infinity. And just a note about the notation here, this set notation tells us which part of the real lines that we're considering, and the square bracket means that we include the number, and the round bracket means that we don't include the number. Similarly for log, the logarithmic function takes positive values of x, but it doesn't take the number 0. So x then must be in the domain 0 to infinity, and that maps onto the whole of the real line, minus infinity to plus infinity. So the domain and range of a function are sometimes important to consider. Mostly we'll just take it for granted, but sometimes you need to think through what's going on. Let's just recap these pictures on a quick diagram. So if I draw in square root of x, looks something like this, and includes the point 0, 0, and if I do log over here, the log function takes all positive numbers and maps them onto the full real line. So that's just a quick recap of some functions that you've seen that are defined in the sort of simplest way as a rule that one can write down that take real numbers and maps into real numbers. Very often, of course, in real life, it's not quite like that. One would be often dealing with data. Data doesn't come as a continuum of the real line, it comes in discrete points. So here's an example of functions defined from data. This is a plot of the global mean surface temperature as a function of time, and the time is measured over years, and you can see the spiky curve that oscillates quite a lot in this picture is the fluctuation of the temperature over time. And then the 5-year running mean uncertainty, as it's written on this curve, is where it's averaged over a 5-year time span, and that produces a smoother curve with less wobbles on it. Functions from data are incredibly important applications of functions and can't be written down usually in a simple form. Other ways to write down functions requires us to write them down in pieces in different sections of the real line. Here's a couple of examples of this. One is the absolute value function, sometimes written as abs or as the modulus of x. Now this is the function, if we write this down as a piecewise function using this curly bracket here, this tells me that the function abs of x produces the number which is minus x if x is negative and x if x is positive. Draw this as a function on a Cartesian diagram. Let's have a look at it. For negative x, in this region here, the function produces minus the value of x. So the number minus 2 maps onto plus 2. And for positive x, it just returns x. So there's a very straightforward example of a piecewise function. Here's an example that we'll use from time to time in physics called the step function. Here I've written as the step function is conventionally written as a capital theta. It's a function of x. And this returns a number 0 if x is negative and 1 if x is positive. Let's just try and sketch this. So it's pretty easy for x negative, it just returns a number 0. And for x greater than or equal to 0, it returns a number 1. Note that we have not included 0 on the lower part of this graph, and we draw this with a circle to represent that we have not included that point. When x is equal to 0, the function is equal to 1, and we emphasize that with a dot at 1. So those are two examples of functions which are defined in a piecewise way, that is, it's split into different pieces with different rules for different pieces of the real line. We get used to thinking as functions and curves as the same thing, but this isn't quite true. A curve can only be written as a function if it has a particular property. Provided a function assigns for each x in the domain of the function only one number, f of x, then it's a function. Yet otherwise, a curve is not a function. Let's have a look at a couple of examples. A general curve then can be written as a function if and only if for each x there exists precisely one f of x. As an example then, let's consider the parabola x is y squared plus 1. Okay, so let's draw what that parabola looks like. Now to write this as a function, we actually need two different parts of it. We need a top part and a bottom part. Because as we see as it's drawn here, each x value actually corresponds to two numbers when we try to draw the curve. So we actually need y equals plus square root of x minus 1 if we want to write it as y equals f of x. And the bottom half is y equals minus the square root of x minus 1. Function at the bottom corresponds to this lower portion, and at the top corresponds to the upper portion. So this particular curve requires two functions to describe it properly. Other types of curves we'll come across are actually often too complicated to write down in the form y equals f of x, and actually require a different approach. This example would be parametric curves. This is where x and y are linked not through a simple y equals f of x type of way, but through a third parameter linking the two functions. So a parameter can link x and y to draw curves. So let's have a look at a simple example of drawing a circle using a parameter to link x and y. If I write down x as a function of t is r cos t, and y as a function of t is equal to r sine t. If I let t be in the range 0 to 2 pi, then this will trace out a circle of radius r. And I can see that if I convert it to the equation of a circle, but by just squaring and adding these two things. X squared plus y squared will equal r squared. Let me just draw a quick sketch of this curve. So this parametric curve then traces out a circle of radius r. And the parameter t is just the angle to the x-axis. As I vary t, this point will trace out the whole circle. Now, to write this as functions then, I actually need to describe the top half of the circle and the bottom half of the circle as two separate functions. So as two functions, the top half is given by y is plus the square root of r squared minus x squared, and the bottom half is given by y is minus the square root of r squared minus x squared. So when we rearrange the equation of a circle x squared plus y squared equals r squared for y, when we take the square root, there are two possible signs, and those two possible signs correspond to the top half and bottom half of the circle.